Okay, we're going to finish up 3.7 here. We'll start with the exercise from the last video. And what we're going to do here is set the numerator and then the denominator equal to 0 and solve for x. And if you do that, you'll get -3/2 from the top, from the numerator, and you'll get 2 and 5 from the denominator. And that breaks up the real line into subintervals, and then we plug in one value in each subinterval and find the sign of our polynomial. Our polynomial here is the 2x plus 3 squared over -x plus 2 and then x minus 5. So for example here, one thing to note, by the way, the numerator, since it's a square term, it's always going to be positive. At least 0, but it's always going to be positive. So all we have to do is check the denominator. And so for p of, you'll notice here, p of -2, well, the top is a positive number. The denominator overall, what do we get? We get 4 times -10. So we overall get a negative number here. If you plug in 0, you get a p of 0. It's a positive number on the top. And then in the denominator, we get 2 and -5. So we have a negative number overall. If you plug in 3, you have a positive number on the top divided by -3 plus 2 is -1. 3 minus 5 is -2. So we have a positive sign here. And if you plug in 5, we get again a positive number on the top. -5 plus 2 is -3. And I'm sorry, we can't plug in 5. 5 is not beyond there. We need to plug in 6. So let me redo that part. The top will still be positive if we plug in 6. -6 plus 2 is -4. And 6 minus 5 is 1. And hence we get a negative number here. So we have overall negatives everywhere, but what we want is just the positive part. So we end up with this part circled in green. So our solution is the interval 2 to 5, and we include the endpoints because we have a greater than or equal to sign. Okay, so notice here we've included the end points. Okay, now we're going to do an example where we have to do factoring in addition to this part. So we're going to do 1 or 2 examples of that, and then we will end the video. So we have this on the top, and x squared minus 5x minus 14 less than 0. Okay, so let's try this out. So notice here, the top can be written as 4x squared minus 7 squared, and the bottom can be factored into x minus 7, x plus 2. So hence the top here becomes 4x minus 7, and then 4x plus 7, divided by x minus 7. Oops. X minus 7, x plus 2, and now we have a full factorization where the numerator is 0 at the points 7/4 and -7/4, and we also have x equals 7 from the denominator and x equals -2. Now what I'm going to do here is I'm going to tell you a little shortcut to this procedure. And this works whenever you have distinct factors. So what do I mean by distinct factors? So I'm going to tell you, so first thing to note in this problem is we have distinct factors, which means we have a single copy of 4x minus 7, which is different from 4x plus 7, which is different from x minus 7, which is different from x plus 2. Now when we have these distinct factors, the sign always alternates. So the sign of this polynomial always alternates. So all you need to do is plug in one of the values. So let's draw our line. Here's -2. Here's -7/4. That's -1 3/4. Then there's 7/4 somewhere here. And there's 7, which lies somewhere down here. Now normally you'd have to plug in, let me rewrite the polynomial here. P of x is 4x minus 7, 4x plus 7 divided by x minus 7, x plus 2. Now normally you'd have to plug in a number in each subinterval. So, -3 might be in this one. Here we'd have to plug in, like, say, -9/5. That's -1 4/5, which is kind of a tricky one. Here's, you could plug in 0. Here you could plug in like 2. Here you could plug in 8, and you do it one by one. But when you have distinct linear factors, it turns out that the sign always alternates. So all I want to do is plug in one sign. So let's just plug in, say, 8. If I plug in 8, what am I going to get? I'm going to get, on the numerator, I'm going to get a positive times a positive divided by a positive times a positive. So overall, we're going to get a positive sign at x equals 8. And I'm just going to say here, now this part's going to be negative. It's going to alternate. The sign alternates. Let's just check that. If we plug in 2, what do we get? We get 8 minus 7, which is 1. 4 times 2, 8 plus 7 is 15. 2 minus 7 is minus 5. 2 plus 2 is 4. So notice here, this is a negative number overall, and that corresponds exactly. And now since we just have distinct linear factors, we just alternate signs. And again, you could check this if you'd like to. At 0, what would we have? We'd have -7 times 7. And then we'd have another -7 here times 2. And this is overall a positive value. So it alternated. And it always alternates. Whenever you have distinct linear factors, the sign always alternates. And this is true for polynomials, rational polynomials, whatever. It's a useful little method to know. So what do we want? We want this polynomial to be less than 0. So we want the places where we have negative signs. We want this piece, and we want this piece. So we want the interval from -2 to -7/4, as well as between 7/4 and 7. This is our solution. Okay. We'll do one last example here, and then we will conclude this video. And the last example is 6x squared plus 4x divided by x squared plus 2x plus 1. And we want this to be greater than or equal to 0. So how do we factor this? Well, on the top, we can take out a 2x. We get 3x plus 2 divided by, and this guy is x plus 1 times x plus 1. So we don't have exactly distinct linear factors here. We almost do, but notice here we have a square term here, and I'll tell you what happens at the square term. Let's do this one the long way, where we plug in numbers in each. Whoops, get rid of that. Let me do this the long way, where we split this into subintervals. So from the numerator, we get 0, and we get -2/3. And from the denominator, we get -1. So these are the zeros of the numerator. These are the zeros of the denominator. So we have -1, -2/3, and 0 here. So we could plug in values like -2, negative 3/4, negative 1/2, and something like 1. Well, what is the pattern here? There's also a pattern here, and the pattern is as follows. So notice the distinct linear factors occur. They're distinct. There's only a single power of x. So at the places where you have a single factor, like x, like 3x plus 2, that corresponds to negative 2/3, versus the negative 1, which corresponds to x plus 1 squared. Where you have, so here you have, this corresponds to the factor x plus 1 squared. Now, whenever you have a square term, this sign, we'll call this sign 1, we'll call this sign 2, those are going to be equal. And then you're going to alternate from there. From there, here you'll alternate, because you have a single factor of negative 2/3, and here you'll alternate again. You'll have a single factor of the x. So this corresponds to the factor x, this corresponds to 3x plus 2. Okay, this is the general pattern. So for even powers, when you have even powers, the roots correspond to no sign change when you go from one side to the other. Whereas for the single factors, you will have the alternation. And let's see that explicitly, at least for part of this, by plugging in these numbers. So let me rewrite the polynomial here. Remember that it was 2x times 3x plus 2. So p of x here is 2x. Let me write this in white. So p of x is 2x times 3x plus 2 divided by x plus 1 squared. Now let's plug in a couple of numbers. Let's plug in negative 2. What do we get? We get negative 4 times 3 times negative 2 is negative 6 plus 4. That's another negative 4 divided by, and remember the denominator is always positive here. This is a positive number. So here we have the sign here is overall positive. And I claim that actually this part is also going to be positive. Let's do that explicitly. Let's compute p of, let's compute p of negative 3/4. Is that the one? Yeah, negative 3/4. What would we get? We would get 2 times negative 3/4 times 3 times negative 3/4 plus 2 divided by, again, a positive term because we have a square there. Doesn't matter what you square, you're going to have a positive term there. So what do we get? We get negative 3/2 on the outside. And here we get negative 9/4 plus 2 divided by a positive term. This is negative 3/2. And if you add these, you're going to get negative 1/4 divided by a positive term. This is a positive number overall. And that is exactly what we expected, that the sign would not change here. So this is, both of these signs are positive. And then we're going to alternate. Again, we'll check that this is true by plugging in the last two numbers. If you plug in negative 1/2, so let's do it over here. P of negative 1/2, what do we get? We'll get negative 1 times negative 3/2 plus 2. And here, notice this is a positive term times a negative over a positive. This is a negative number. Negative. It's not negative 1 necessarily, but it's negative overall. So p of negative 1/2 is a negative number. And that corresponds to alternating from positive. We're going to get a negative here. And we're going to get overall a positive here. So let's just check that last piece, that p of 1 is actually positive. Well, what is it going to be? It's going to be 2 times 5 divided by 4, which is a positive number. So indeed, it did follow our pattern. So we have positive, positive, negative, positive. We want where this thing is greater than or equal to 0. So what we want, and let me use a different color, what we want is we want this piece, we want this piece, and we want this piece. Okay, so we want everything below, so the solution is everything below -1, as well as everything between -1 and -2/3, as well as everything beyond 0. Well, notice that these parts actually combine into a single interval. So this is actually just -infinity up to -2/3 union 0 to +infinity. And that is our final solution. Okay, so these are some examples of ones where you have to first factor. I've also introduced the idea of what's called distinct linear factors, or even powers, where signs don't change. If you have single factors, the signs do change, and that kind of helps to prevent spending so much time plugging in numbers in between. Okay, so this is the end of 3.7, as well as the end of chapter 7. Chapter 3. And so in the next video, we will begin the section on chapter 4.